chapter 21 here, which is nuclear chemistry. So let us get into it here. So nuclear chemistry obviously involves radioactivity. Pretty much radioactivity is sort of the emission of energy through space in the form of waves. Radioactive nuclei, they do spontaneously decompose into smaller nuclei. When that happens, that is what's referred to as radioactive decay. If you look on the periodic table, a lot of the sort of lower elements there in those two rows are radioactive sort of elements. When we do have sort of decomposition that occurs during nuclear decay, unlike sort of a chemical reaction, as we'll talk about, the nuclear decay really does involve, like it sounds like, really the particles that are in the nucleus. So here, unlike a traditional sort of chemical reaction where really electrons are involved, here in nuclear chemistry, protons, neutrons are basically involved in the process of these sort of reactions that we'll talk about. The sort of starting nucleus is sometimes referred to as the parent nuclide, and that is the nucleus that's undergoing sort of radioactive decay. As it goes through the decay process, the sort of new nucleuses that are formed are sometimes referred to as the daughter nuclei. As I mentioned before, if you go to periodic table, kind of above 84 protons are pretty much everything that is sort of radioactive. There are different types of radioactive decay and sort of particles or rays that we'll talk about. Rutherford, you remember Rutherford, he did some things with gold and some foil, right? He shot some alpha particles or alpha rays. Alpha rays are very common in nuclear chemistry. They have the symbol of alpha with a 4 and a 2. They also are really the helium nucleus. So for alpha particles, it is very common as well for people to just use helium there to represent an alpha particle. So you'll see both sort of nomenclatures used for alpha particles or alpha rays. They basically have a mass of 4 and an atomic number there of 2. Beta rays or beta particles are also very common. They're also have a couple different symbols that we see. The beta symbol, are there really like an electron? So sometimes just an E is used to represent those guys as well in sort of nuclear reactions. And gamma rays, which are really just kind of pure energy. If you remember from the electromagnetic spectrum, they are the furthest there on the left. They have the shortest wavelength, which means they have the highest energy. They're really just pure energy that's given off. These are sort of equivalent to the particles that we find sort of in a atom, right? Kind of positive guys, negative guys, and guys with no charge, right? Our protons, electrons, and our neutrons that we have there. In addition, there's some other type of particles that are very commonly sort of seen. We'll see something that's known as a positron. And that's like an electron with a good attitude. It has basically the same symbol as a beta particle, but it is positive one instead of negative one there. We'll see some reactions that they undergo when we have unstable nuclei. Sometimes they'll do what is referred to as electron capture. And we'll talk about some of the terminology in terms of reactions for nuclear chemistry. By the way, when I do write a number up on top and on the bottom there, right? The top number is, that's the mass number, right? Bottom number is the atomic number. Atomic number is the number of, not everybody at once, protons, yes. Mass number is the number of protons and neutrons, right? So those numbers are really important in nuclear chemistry, especially when we talk about balancing equations. We use those numbers a lot in our symbols as well. So as we just saw there, again, our atomic number is the number of protons. The mass number is the number of protons plus the neutrons. If you take the mass number minus the atomic number, right, that gives you the number of neutrons there are. Can you find both of those numbers on the periodic table? No, the only number you can find on the periodic table is the atomic number, which is the number above the symbol. The mass number is not found on the periodic table. The guy on the bottom there is the atomic mass, which is different than the mass number. When you calculate atomic number, mass number, number of protons, electrons, or neutrons, those all should be whole numbers and positive whole numbers. And if you look obviously on the periodic table underneath each symbol, pretty much none of those guys are whole numbers, and that's the atomic mass, which again is different than the mass number. So useful a lot of times in this chapter is the periodic table, because you can use it to figure out obviously the atomic number, which is the number of protons, which obviously can be helpful as you go through some of the balancing. Now we saw some symbols a second ago. Here are some other important sort of symbols that come across a lot here in nuclear chemistry. The proton is also used a lot, and that also has a couple of symbols which are commonly used. A P for a proton has a mass number 1, atomic number 1, or just hydrogen, which is also a proton, is used. Neutron has a 1 for the mass number, 0 for the atomic number, and this is really our beta particle here. And our positron, as you can see, carries basically the same symbols, but it is +1 versus -1. In terms of the difference between these two in sort of problems, there usually is some distinction to tell you that it is a positron. So if you see just the beta symbol by itself, it is probably safe to assume that it is beta that they're talking about. They typically will put something in there to let you know it is a positron. So sometimes they'll even just kind of put a plus up there on top, or as you see down there, they'll do the +1. But there'll be some indication usually that it is the positron that they're talking about, if it is not the beta particle. But again, if you just see sort of the beta symbol, it is probably safe to assume that it is the beta particle. Like I said, they will usually put some type of positive guy there on the positron to indicate that it is obviously a positron that they're talking about. Also, again, as I talked about, there are a couple of symbols for our alpha particles, and again, both are very commonly used. It is really important to know the symbols here, and also the mass number and atomic numbers that go with it, because it will help you when you're balancing equations and stuff like that, if you know what these particle sort of symbols and numbers are. Any questions on that there? So when we talk about radioactivity, different types of particles will, as they are emitted, travel further. So as we can see here, alpha particles, so something decays through alpha emission, that means that it will give off an alpha particle. It only goes about 0.01 millimeters into lead. Beta particle, as you can see, travels a lot further, and a gamma ray travels much, much further through things. It's really important, if you should ever find yourself working with radioactive material, that you know what type of emitter it is, what type of particles that it gives off, as to what type of protection that you may need. Sometimes you just need a lab coat, other times you need lead and some concrete barriers and stuff like that, and shields, depending on what type of emitter. So it's really important to always check that out for yourself. Sometimes people aren't very informative about what you're dealing with. So again, depending on really the type of radioactivity that it's emitting, as to the level of protection that you need to sort of safely-ish work with it. Here's some more symbols. Again, we pretty much saw these guys here, so we'll roll with this. So let's talk about balancing nuclear equations, which is like super hard. So when we balance nuclear equations, pretty much you need to know how to add, but other than that, that's all you need, and a periodic table. So when we have a nuclear equation that is properly balanced, unlike a chemical reaction that occurs when we have conservation of the elements, in a nuclear reaction, there is no conservation of elements. So in a normal chemical reaction, right, to balance the equation, we put coefficients. We have like 4 carbons on the left, 4 on the right. Everybody's nice and balanced. But in a nuclear reaction, there is no conservation of those elements because protons change, neutrons change. So as the element changes, we make new elements as it goes through a decay process. So to balance the nuclear equation, pretty much what you need to do is make sure that all the mass numbers on the left-hand side equal all the mass numbers on the right-hand side. So if we do a quick counting there, on the left, we got 235 and 1, which is obviously 236. And on the right there, we got 138, 96, and 2, which also gives us a 236. So this reaction would be balanced in terms of its mass number. We also need to basically do the same thing for the atomic numbers. So the numbers on the bottom here all need to basically add up to each other as well in order for this equation to be properly balanced. So 92 and 0 on the left is 92. And obviously there on the right, we got 55, 37, and 0. So that will get us 92 on the right. So because there's no conservation of elements in a nuclear reaction, that is because out of all the particles that an atom has, protons, electrons, and neutrons, which one is the most important to tell you which element it is? It is the protons, which is the atomic number, right? So if you look on the periodic table, there is no atomic number that repeats. So every individual element has its own atomic number, our number of protons. And again, since these reactions really do involve protons and neutrons, which are in the nucleus, as those protons change, we get new elements. So what would happen in a situation like this is perhaps one variation of this would be, say you were not given this guy, and maybe you want to figure out, what this guy would be. So obviously what you would do is you would count up the mass number on the left and go, I got 236 there on the left. You would then add up the mass numbers on the right, which would be 138 and 2, which would give you 140. When you subtract that, that is going to give you your 96, which is the missing mass number. More importantly would be what we got going on the bottom here. You would do the 92 for the atomic number on the left. Here we would have 55 and 0. So minus 55. And obviously that would give us our 37, which would be our atomic number. You would go to the periodic table, look up number 37, and you should see RB next to it. And again, that's how you would figure out pretty much your missing element. So in a lot of these cases, you will use that atomic number and the periodic table to figure out what's missing. I would say in a lot of cases, it is an element, but what could be missing in a reaction could be a particle. So, if you could be like an alpha particle, a beta particle, or something like that. So that could also be missing. Also, when we talk about nuclear sort of reactions, there's a couple of terminology that we sometimes come across. So when we think about sort of the equation and the arrow, if something is going through some type of decay or it is giving off an emission, all of those things mean those particles end up on the product side. So anything that is going through some type of decay process, doing some type of emission or something like that, those particles will go there on the product side. When we have something on the reactant side, that is usually some type of electron capture, some type of bombardment. Like you bombarded this atom with some neutrons or something like that. So those particles would end up on the reactant side. So most of the time, the particles would probably end up on the product side, but there are a couple occasions where you would have maybe a particle ending up there on the reactant side. And again, that's usually a situation where they talk about bombarding some type of capture or something of that nature. So for example, here, if we were to do this equation or this reaction, we would look at PO 212, and that's what we would start with. It decays by alpha emission. So alpha emission means it's going to give off an alpha particle, which you could represent with the alpha symbol with the appropriate 4 and 2. You also could have used helium as well, which is again an acceptable sort of guy for our alpha symbol. If you're not sure, you would then go to the periodic table, you would find PO, and that would give you the atomic number from the periodic table, which is 84. At this point, we're really thinking about what is missing here, which is what is the new sort of elements that's going to form. So we could start with our atomic number. We have 84 on the left. We basically have 2 on the right. So if we subtract that, that means 82 is really our missing atomic number here on the right-hand side. You then would go to the periodic table and look up number 82, which is lead. And obviously for our missing mass number, we would do the same. On the left-hand side, we have 212. On the right-hand side, we have 4. So subtracting that, going to give us a 208 as our missing mass number. So at this point, we have basically 208 and 4 up on top, which is just 212 on the right and 212 on the left. And obviously 84 on the left and 84 on the right on the bottom will give us our balanced atomic number. So this would then be our balanced nuclear equation. Any questions on that? Yeah. What's that? Yeah, this is like super easy. You just got to add to have a periodic table pretty much. Yeah. All right, now you're gonna add water to it. No, I'm just kidding. No, it's pretty simple, really. Periodic table and finding that atomic number will pretty much give you your element, and then you basically add in what's missing for the other parts. It was sarcasm, yes. Other questions on that? All right. So as we talked about a little bit here, there is a really big difference between, say, chemical processes and nuclear processes as well. Again, in a chemical reaction, a typical normal chemical reaction, it really is all about breaking bonds and making bonds, and that's pretty much all electrons. That's pretty much what's all involved there. And really, nothing changes in the nucleus in a chemical reaction. So that's why in a traditional chemical reaction, when we balance an equation, we got like 6 carbons on this side, we end up with 6 carbons on the right-hand side. They may be in different sort of compounds, but we don't lose any elements. And very different than that is in a nuclear reaction, as I mentioned, pretty much everything happens in the nucleus. So our nucleus is really changing, the protons, the neutrons, and it's really those protons that's really important as it goes through a decay process. Those protons really start to change, and as those protons change, that means that we are going to obviously get new elements that are going to be formed. So there is absolutely no conservation of elements in a nuclear reaction. You always start and end with pretty much different things as it goes through a continual sort of decay process. So just to look at some of these processes here and what's really happening in each of these cases, or in some of these cases here. So when we go through a beta decay, and in this case, the beta decay, there's our beta particle in both of these examples here. We don't have to worry about this guy too much in here. That's a neutrino. It pretty much has 0 for the mass and 0 for the atomic number. We're not going to worry too much about those guys. But in this case, basically what we have going on here is we do have 7 and -1 for our beta particle on the right, which gives us 6, which matches our 6 over there. And we have 14 and 0, which gives us our 14 up on top. What is really happening in this sort of beta decay is actually a neutron is becoming a proton and giving off that beta particle. So that's why it's emitting it. So although it looks like obviously the mass number doesn't change, it actually does change along the way in this particular case. If you just sort of follow what's happening. So for example, and it's sort of a step-by-step process, if you will. In this case, basically a neutron is going to be lost. So we're going to lose a neutron, which is 1 and 0, which takes our number up on top to 13 and 6, if you will. As it does that, is then going to form a proton, which has a 1 and a 1 in terms of this number here, which takes us to 14 and 7 in terms of our number. And here also give off obviously a a beta particle here, which has R 0 and -1. So although it does appear that this number here doesn't change, it actually is sort of changing. We're just kind of gaining a proton along the way there, which does change back the mass number and the atomic number to 14. So it ends up being the same for the mass number, even though there is really a transition that is occurring along the way. So in a beta particle, a neutron is really being converted to a proton. So by gaining an extra proton, what happens is we actually need to go forward in terms of our atomic number, right? So we actually go 1 forward there because of the negative. So we go from carbon to nitrogen as it gains that proton. And a positron decay, same thing sort of happens here. Our mass number really doesn't change overall, but it does sort of change. But we do have our positron, which means in this case, we're actually going to lose a proton. So in this case, a proton becomes a neutron in this particular process. So if you just kind of follow the numbering, we start with a 11 and 6. It loses again here a proton, which is a 1 and a 1, which gets us to a 10 and a 5. The process though then gains a neutron, which gets us to 11 and 5. Which is on this example where we end up, and obviously giving off our positron particle as a result of that as well. So again, sometimes it may seem if you just kind of look at the overall numbers that nothing much is changing in some cases, but again, there is some change that's occurring here. We're losing, for example, a proton, but gaining a neutron, or in the top case, losing a neutron, gaining a proton. So overall, math-wise, it sort of evens out for the mass number, but the atomic number is obviously affected overall in terms of the change that occurs. Electron capture is pretty much what it kind of sounds like there. The electron capture puts our electron on the reactant side. And in this case, an electron and a proton come together in this case, and that gives us basically the formation of a neutron. We just do the math, we're left with 1 and 0 basically when those guys come together. So overall here, what we see is we do see an actual, whoops, come back. We do see that the mass number overall will not change. And in this case, we will see that the atomic number does change. Atomic number changes because we do lose a proton, but by gaining that neutron back, it balances out the mass number up on top. So again, overall, it doesn't change. The biggest sort of change that we do see is alpha, which gives off, again, our alpha particle, which has that 4 and 2 sort of change that occurs. And fission, spontaneous fission. Fission, in a sense, is the process where a unstable sort of nucleus will split off into 2 new nuclei, and it will also give off some neutrons and also give off some energy in the process of doing so. Fission is basically that splitting into those 2 new nuclei. It could happen spontaneously, or you could actually kind of force it to happen by shooting a particle at a stable nucleus, which makes it unstable and kind of kicks off that reaction to basically occur. And we'll talk a little bit more about fission later on as well as we go through it. All right, so here's just a chart similar to one you have in your book of all the changes we just talked about. All right, so one more time here, let's try this one here. Write the nuclear equation for the positron emission of potassium 40. Or I'll pass some periodic tables around. Like, so everybody doesn't strain their neck trying to look at the big thing. There you go. Okay, let's take a look. So by the way, when the symbol is written like this with a 40, that is the mass number, right? So that is the mass number, a very common way. We know it's not the atomic number because we could go to the periodic table and find the atomic number, which is number 19, I believe. In this case, it's going from a positron emission. That means our positron particle will be on the product side. So that's going to be a 0 and a +1. And again, whatever you would like to use, either the beta symbol or the E is all good. In this case, we just really need to find the missing atomic number. So to get us to 19 on the other side, that looks like 18 is what we need. Once again, we could go back to the periodic table there, and 18 is argon. Up on top, we have 40 and 0. So 40 would be there. There we go. Any questions? Okay, let's take a look here and see. So first one is uranium-238. So it's going to be uranium-238. Looking at the periodic table, is going to emit. So again, anything with emission or emitted up here on the product side. Again, you can use the alpha symbol or the helium symbol, whichever one you like. Our missing atomic number in this case would be 90. And again, going to the periodic table, number 90 is TH. Up on top, we basically have 238 on the left, 4 on the right. So that's going to be a 234 up there, up on right. Any questions on that one there? Coming to neon 24. Again, 24 would be our mass number, goes up on top. Neon there is 10. Once again, it's an emission, which means our beta particle there will be on the product side. In this case, though, it is 10 on the bottom and -1 on the right, which means we do need to go one more as we gain a proton here to 11 to balance it out. That gives us to sodium in this case. And up on top, 24 would get us all balanced. Looking at the next one, which is nitrogen 13. Nitrogen there from the periodic table is 7. Once again, it's an emission, which means the particle will end up there on the product side. Again, you can use the beta symbol there, or you could use the E with the +1. In this case, we have 7 and 1, which means 6 would be our missing number there. And that goes for carbon and 13 up on top. Any questions on that one there? Lastly here, we got electron capture. So we have Be7. Beryllium there is 4. Electron capture means that that's going to actually be on the reactant side, like it's being captured. So we're going to do an electron over there, like so. There you would want to use, obviously, just probably the E for the symbol for the electron, since it is an electron. Here we got 4 and -1, which gives us 3, which should be lithium. Up on top there would be 7 in this case. Yeah. Any questions on those? Yeah. So on which one? I'm sorry. Uh-huh. That is are you talking about this graph here? Yeah. So yeah, what it's talking about here is actually the change that occurs. So in that beta situation, that is where we will gain a proton from a neutron changing. So that's what changes. But the actual symbol is right here. It's basically that one is the symbol for it. Yeah. So these two columns on this table talks about how the mass number and the atomic number changes through the process, basically. Yeah. But definitely a beta particle would be like we have here. So what it was talking about there is this process in a beta decay, a neutron changes to a proton. So that's why I said you gain basically a proton is what that table was saying in that case. Yeah. But the actual symbol should definitely be -1. Yeah. Other questions? Okay, so obviously you need to know how to balance equations. Like I said, periodic table is your friend, and also understanding the charge, the mass number, atomic number for those symbols or those particles, also really important as well. We're now going to talk a little bit about stability and stability of nucleuses and nuclei. And one really sort of important way that we look at stability is what is sometimes referred to as the N to Z ratio, N being neutron, Z being atomic number. So really our neutron to proton ratio. And the ratio of neutrons to protons is important, really measure stability. And there is sort of an acceptable sort of ratio where, you know, things are pretty much stable. And then you could find yourself having a ratio that is too high, which would be, say, on this side of that stable sort of ratio. And if you find yourself with a too high ratio, what will happen is neutrons are converted to protons via a beta decay. So what will happen is if it's too high, the element will basically go under a beta decay in an effort to convert those neutrons to protons and kind of bring itself kind of back down to a more acceptable level and a little bit more stable level. Will it happen all at once, and will just one sort of beta decay basically move you to a stable arrangement? The answer is no. It may, or it may not, but what it will do is kind of move it closer to a more stable ratio that will happen. If the ratio is too low, which means you're kind of on this side of that kind of nice, happy ratio, protons are converted to neutrons, and that basically will move you sort of back up towards a more acceptable ratio. Once again, it may not result in a perfect stability after one sort of process, but it should move you there. It actually will go through two different routes to get there. It can, which is a positron emission or an electron capture. So both will kind of get you to the same end result. It can't go through an alpha decay, but it's not as efficient. So for this type of situation, we will go with one of these two situations that will occur. Just to kind of show you, we just saw a electron capture here of beryllium-7. So we just did beryllium-7 with our electron capture. And if you did the electron capture like we did before, you end up with 3, 7, and lithium. Now, if you did a positron emission, starting with the same thing, positron emission would mean that we have that going on, which would mean that we would end up with the exact same end result. So either one of those processes will result in really the same product being formed. So you could go with either one for the ratio being too low. So how do we know what sort of an acceptable ratio for our neutron to proton ratio. It was sometimes referred to as the valley of stability, or sometimes the belt of stability. And that's the sort of yellowish line there where we have a nice ratio of stable elements. If your atomic number is somewhere between 1 through 20, a stable ratio is a ratio of 1. From 20 to 40, the ratio goes up to 1.25. From 40 to 80, a ratio of 1.5 is sort of stable. Anything above kind of 84, as we talked about, is pretty much not going to be stable. They're going to be radioactive nuclei and will decay. So you could use these as your cutoffs, kind of 1 through 21, and then 20 through 40, 1.25, 40 through 80, 1.5. Now, there are some gray areas and areas where it sort of bleeds over, if you will. Obviously, this guy ends at 20. This guy starts at 20, and this one obviously ends at 40. This one starts at 40. So there is sometimes in books sort of a gray area where they'll go, well, it's like 20, but you know, it's above 1, but it's less than 1.25. So that's still going to be okay because it's kind of in that little grayish area. So to try to avoid some of that for our class here, what we're going to do is we're just going to use these as sort of really hard cutoffs. So either it is that number, or if it's not, then it's too high or too low. You could use up to 20 for 1 if you like. Okay, let's take a look. So magnesium 22. Again, we could go to the periodic table there and find 12 as our atomic number. That means really the number of protons there would be 12. Our number of neutrons would be our mass number minus our atomic number, which would be 10 in this case. So our N to Z ratio would be 10 divided by 12 gives you 0.8333. In this case, we have an atomic number of 12, which falls between the 1 to 20 range. And an acceptable ratio would be a ratio of 1, which would be stable. In this case, 0.833 is a little bit on the low side there. That means that it will go through one of two things, either a positron emission or an electron capture. That means that we would have 2212 magnesium. If we did an electron capture, it would give us an 1122 and a sodium. Or it could go through a positron emission, which would also get us an 11 and a 22 and sodium in this case. First off, any questions on that there? At this point, we could see that we were too low, so we were kind of on the low side. So what we should have done should move us kind of closer to the valley of stability. If we do it for what was just formed here, the number of protons is 11. Number of neutrons is 22 minus 11, which is also 11, I believe. That means our N to Z ratio is 11 and 11, which is 1. So in this particular case, it actually moved us to a really stable situation. Again, it will not always, after, say, the first sort of decay process, move you perfectly stable, but it should definitely move you in the right direction in terms of the ratio. Any questions on that there? Okay, so here we do have krypton, which is 85. Going to periodic table there, looks like a 36 for our atomic number. That means our number of protons here going to be 36. Our number of neutrons, our mass number, which is 85 minus 36. So that is going to get us a 49. So our N to Z ratio here would be 49 divided by 36. That's like a 1.36. Now we do have a atomic number here of 36, which would fall in that kind of 20-ish to 40 range, which acceptable would be a ratio of 1.25. This looks like it's going to fall on the high side there. So that means it is obviously radioactive in this case. It also means that it will go through a beta decay here to sort of fix that. So our beta decay would be our 8536. Again, beta decay would give off the beta particle, going to leave us with a 37 that is necessary there, as we do gain a proton in this case, and 85. Going to periodic table, 37 looks like RB in this case, and that is should be obviously the new nucleus that should be formed in this case. Any questions on that there? Once again, we could see if we were in this case too high, we should have moved back towards the sort of belt of stability. So if we take a look at our RB, the number of protons here would be 37. In this case, the number of neutrons would be 85 minus 37. Gets us 48. So we would have 48 divided by 37. Gets us about a 1.3-ish type of ratio. Again, it is down from 1.36, and we are moving in sort of the right direction. Once again, it will not always perfectly get you to that right ratio, but it should obviously be moving sort of in the correct direction towards it. Any questions on that there? And if you did have a problem like this, you wouldn't need to keep going until you got the perfect ratio or anything like that. You would just do, obviously, the first reaction that we did here would be sufficient. Any questions on neutron to proton ratio? All right. There we go. Now, that is one important measure of stability and one that we use a lot. There are other things that we do look at sometimes to think about sort of stability. And besides the ratio, a lot of the most stable nuclei will have even numbers of protons and neutrons. As you can see from this table, that is pretty much your sort of best combination. Is even protons, even neutrons. There's like 157 stable nucleuses that have that combination. Really, your next best ratio is like even protons, odd neutrons. Got about whatever it is there, 53 stable ones. Your next best situation, odd protons, even neutrons. And really your worst in terms of stability, if you were just sort of quickly trying to decide stability, is if you have something that has an odd number of protons and an odd number of neutrons. For the most part, there's very few stable nuclei that have that sort of arrangement. Also, if the number of nucleons add up to a magic number, the nucleus is more stable. Nucleons is also something that you hear a lot of in nuclear chemistry. Nucleons are pretty much your guys in the nucleus, right? So those are your particles in the nucleus, which are basically your protons and neutrons. So nucleons are really like your mass number. It is the particles that are found in the nucleus. So it's the same idea as when people sort of reach noble gas configuration. That's a really stable sort of configuration. So a lot of times, most stable when either a neutron or a proton has 2, 8, 20, 28, 50, 82, and your Powerball is 126. Just play those numbers later. So those are some stable sort of arrangements. I would say in a lot of cases, most of the time, people will look at either the N to Z ratio, this sort of arrangement for stability, and as we'll talk about a little bit later on in this chapter, binding energy is another one that people use to help determine sort of stability, is sort of the binding energy that we see. Now let's talk a little bit about decay series. A decay series is basically one radioactive nuclei basically changes into another. And again, the sort of parent is the starting one, the daughter is the one that comes after that. And a series is basically this process that continues until basically a stable nuclei has been reached. And that's what is referred to as a decay series. Now, there's a couple ways you could do a decay series. You basically can just simply write out the equations like we just did before when we were balancing the equations. The product of the first equation would be the reactant in the second equation, and you kind of continue that process where the reactant goes to the product then becomes a reactant, and you continue that process. Now, if your decay series involves beta decays or alpha decays, and you're really just sort of interested in maybe what you get at the end of the road, at the very end, and you don't want to write out each individual equation, you can kind of shorthand it with some math. For every alpha decay, you subtract 4 from the mass number, and you subtract 2 from the atomic number. And for every beta decay, you basically will add 1 back to the atomic number. So if you want to kind of quickly do it, you could kind of subtract those off from the mass number and the atomic number. And you can figure out what comes at the end, or you can basically just figure out it through each process. So for example, if we took uranium, say uranium-238, and we want to know, hey, what do you get after it goes through an alpha, beta decay sort of situation? We'll do just a short little decay process here. So one way that you could do it is simply just start out with your equation like we did before, which would be uranium-238. Again, periodic table and see uranium is 92. The first thing that would happen is we would have an alpha decay, which means we would have our alpha, which means we would end up with 90 and 234 going to the periodic table. 90 is TH. So that would take care of the alpha part. The next thing that would happen is the product here would be our starting guy. And that guy would then go through an alpha decay process, which means it would give off an alpha particle, meaning in this case, we're now down to 88 and 230. And in this case, 88 on the periodic table there is RA. That would be the sort of the second step in the process. We then would take this guy, and he would then go through the next decay process, which in this case of my made up one would be a beta decay, which means we would do our beta particle, which means we would gain a proton and go 89 and 230. Again, 89 here would be AC. Then lastly, in this short little decay series, we would take our 230, 89, and it would go through one more beta decay, and that would get us to a 90, 230. And again, 90 here would put us back at TH. So this is one way that you could do a decay series. Basically, just write each individual reaction up and basically can figure out what you would get along the way. Now, if you were just interested maybe in what you would get at the very end of this process, you could use this sort of math approach. And the math approach would be something like this. We have 238 and 92, and we have 2 alpha particles. That means we're going to take 4 and 4 away. We're going to take 2 and 2 away. And we have 2 beta particles, which means we will add 1 back here and add 1 back here. That gives us on the top 230, and on the bottom 92 minus 2 is 90, minus 2 more is 88, plus 2 is back to 90. And you could get to the end product here by just doing that. So again, if you're not maybe interested in each individual step and what you produce in each individual step, And maybe just what at the end, you could kind of take that math approach and kind of get there a little bit quicker. Any questions on that there? Now, normally in the decay process, unlike the short one here, it would continue until some type of stable nuclei is basically reached. And if we look at uranium, here is actually the decay series for uranium. It actually splits off in two subs. We have alpha, beta, and alpha. And it will continue down until basically it hits lead 206, which is a stable sort of approach. And again, you could get each of these products by doing what we just did on the previous slide, either writing the equations or sort of doing the math approach to it. So let's talk a little bit about kinetics and radioactive decay. It's a good review coming up here for the final. So pretty much all radioactive decay follows first order kinetics. We remember first order kinetics, that's our favorite. That is the natural log of A, right? Equals the natural log of A naught minus KT. That is the half-life is equal to the natural log of 2 over K. And that is our favorite graph ever, which is the natural log of A versus time yields you a straight line where the slope equals minus K. We remember all that stuff, I'm sure. But pretty much all radioactive decay will follow that first order kinetics, but sometimes they will use some different symbols because it's nuclear chemistry. So they'll use N for nucleide instead of A, for example. One other thing that's also a little bit different than what we did before in terms of kinetics is typically when we did kinetics, we would use concentrations here. And you can use concentrations, but frankly, you can use any unit you like. So you could use grams, you could use milligrams. You could also use rates in there as well. So rates of radioactive decay is also used in there. So as long as the units are the same on both sides, you really could use anything. You don't have to necessarily use molarity in there for the A part of it. You could use anything really, grams, milligrams, rates of decay. So sometimes they'll use that as N. Also, the K, which we call the rate constant in kinetics, is what is referred to as the decay constant. If I can write that, decay constant in nuclear chemistry. And sometimes it is also, in some books, lambda is used for the decay constant. So they'll sometimes use lambda as the symbol for the decay constant. And like I said before, again, T is time in this case, and you do want to watch out units. The half-life is the natural log of 2 over K. That is where the 0.693 comes from. If you remember, you take the natural log of 2, that is 0.693. So here again is that lambda, which is the decay constant here, which is really like your rate constant. Again, that is time. And again, they use sometimes nuclei as well. Again, we see the same type of graphs that we saw with first order kinetics. Works the same way, except again, a reminder that you very often do need to use both equations together. So very often you do need to use the integrated rate law and the half-life equation really together. So that is, both of these guys are usually used a lot of times together in nuclear chemistry. So when we talk about half-life, that obviously is the time it takes for half of whatever you start with, basically to decay and go away. So, you know, if you started with 6, you got 3 left. And after that, obviously you keep dividing by 2. Some things have very long half-lives. Some things have very short half-lives. You can see here, uranium has like a half-life of 4.5 times 10 to the 9 years. That is a super long time. Carbon-14 is 5730. But you can see some things are very quick in terms of their half-life. So radon is 55.6. So it does go away very, very quickly, usually about 10 half-lives or so. You are pretty much done with it. Not much is left at that point. So let's try one here. If you have a 1.35 milligram sample of plutonium-236, calculate the mass in milligrams that will remain after 5 years. The half-life of plutonium will go with 2.86 years. All right, so take a few minutes here and see what you come up with. It's always going to be first order, so we really always know the correct sort of formulas to use here. And you can use really the same ones as we used with kinetics. If you want to use the nuclear symbols, you can, but it's basically the same thing. We'll use our half-life equation as well. So in this particular case, we have 1.35 milligrams, which is our initial. And we want to know what is our final there at the end after a run of 5 years. So if we just look at sort of our equation here, we do have our time. We are looking for this guy. We do have that. We are missing the decay constant in this case, and that is really where the half-life comes into play. So as I mentioned before, a lot of times in nuclear sort of kinetic problems, you will need to use kind of both equations together because they really oftentimes will give you a lot of half-lives. We can use the half-life equation to get the decay constant. So that is where we're going to start. So the decay constant would be the natural log of 2 divided by our half-life, which would be the natural log of 2 divided by 2.86 years. That is going to give us this gives us, we'll call it 0.242 reciprocal years. If you remember the first order kinetics, right, the rate constant has units of 1 over time, right, which is basically what this is. So that all matches. By the way, you should also remember that you should watch the units of K and time to make sure they are in the same units. In this case, they're both in years, so that's good, but they could be in different units. So you want to make sure that they do agree. That would then give us the natural log of A, which is what we're looking for, equals the natural log of 1.35 minus the decay constant we just calculated times our years, which will also cancel out because we have everybody in the same units. That is going to give us the natural log of A. And if we clean up the right-hand side there, we will get natural log of 1.35 minus 0.242 times 5, something like negative 0.909895. To get rid of the natural log, we got to E both sides. Right, those guys get rid of each other. That leaves us A is equal to we'll call it 0.403. The units here would be the same as our other guy, which was milligrams. Any questions on that? Yeah. What's that? You do not. So unlike kind of what we used when we did regular kinetics problems, it definitely wasn't molarity, which obviously you could, but very common in nuclear chemistry. You'll be given something like this, milligrams or grams are also very common as well. You'll be given a rate, like how many, grams per second or something like that. Some type of rate of radioactive decay is also used. So kind of an initial rate and a final rate is sometimes used as well. So really in that equation, as long as the two A's are the same units, you should be okay. Now, other questions on that? All right, so let's take like a 30-minute break there and we'll come back. We'll do a couple more examples and call it a day here. So 5 after 10 should be good. Stretch your legs, go outside, see some nature, whatever you like. Okay, let's take a look. So once again, we're going to use our kinetics formula here. And our our half-life as well. So again, in this case, we are given the initial of 10.24 grams. We are once again looking for our final. We know the time is 5.4 weeks, and we know the half-life there is 3.8 days. So once again, we do need to use the half-life equation to get the decay constant. We do have some unit differences here, so at some point you do need to get them into the same unit. I'm just going to convert this into weeks. Why not? There are 7 days in a week. That would get us 3.8 divided by 7, 0.5429 weeks. So using our half-life equation here, natural log of 2 divided by 0.5429 weeks will equal our decay constant. So we take the natural log of 2 and divide it by that number. Gives us a decay constant about 1.2, and we'll call it 8 reciprocal weeks in this case. Yeah. Any questions on that there? Now that we have that, we do have everything on the right-hand side here to plug in. So that gives us the natural log of our initial minus our 1.28 weeks. And since I converted it to weeks, that will cancel out nicely with the weeks that are here. Otherwise, you might want to convert the weeks to days, whichever way you want to do it. The weeks should cancel, and that will get me the natural log of 10.24 minus 1.28 times 5.4. Going to give me the natural log of A equals minus 4.585698. Going to do an E of both sides there. And that will give me then that we are going to end up with 0.0102, and there would be grams in this case. And again, that's less than what we started with, which is good, right? Obviously, if you ended up with more, that would not be good in that case. Any questions on that there? So really the same sort of kinetics type problems that we've seen before. Again, just slight differences using some different units, and also a lot of times that half-life equation does need to be sort of used together with the integrated rate law. Any questions on that one there? Okay. All right. Go through that. That's the one we just did. We can also use kinetics and the idea of half-life to understand dating and radioactive dating. For example, we could use radiocarbon dating. In this case, we would follow obviously how much carbon sort of decays, where we'd use the half-life of carbon as 5730. Uranium-238 dating is also used, produces some lead as a byproduct, and the different combinations there of before and after will also help us determine how old something could be. Half-life of uranium, 4.5 times 10 to the 9 years. So if we look at a problem like this, an ancient skull gives 4.5 disintegrations per minute per gram of carbon. So that is what that whole thing is right there. That is disintegrations per minute per gram of carbon. That is not Celsius. That is actually per gram of carbon. It's basically a rate of radioactive decay. The importance of that is it tells us it's carbon, which means we would want to use the half-life for carbon here for doing some type of dating. So that would be 5730. Okay, let's take a look. So again, we'll use our equations here, our first order kinetics. So here we have our skull that gives 4.5 disintegrations per minute per gram of carbon, and a living one. So I'm going to go with living as initial. Yes, much like life, friends, 15.3. Ending is like death there, which is 4.5, right? So that's how we would know those guys. We want to know, in this case, time. So once again, we are still missing the decay constant. So much like we did before, we are going to use our half-life equation. And again, that's where the grams of carbon come into play, that we know that we should use really sort of carbon 14. There's half-life. So using that like we've done before, we will solve for our K, which would be the natural log of 2 divided by the half-life here, which is 5730 years. That will give us a decay constant here of 0.000121 reciprocal years. Now, putting in our numbers here, we have the natural log of our final minus the equals the log of our initial, 15.3, minus our 0.000121 years and our time. I personally am going to take the natural log of 4.5 and then subtract the natural log of 15.3. So natural log of 4.5 minus the natural log of 15.3 will get me negative 1.223775 equals negative 0.000121 reciprocal years times time. And then I'm going to divide that to the other side. And when I divide that to the other side there, I end up with about 10114 years as my time. And I guess if we were going to be a significant figure-ish, maybe 10100 years. Yes. About 10,000 years old, give or take a year or two. Any questions on that one there? Yeah. Yeah, so you don't need to in this case, because really when we do this part, as was the question before, when you do subtract like the natural log of something, a minus the natural log of a naught, that's really like dividing those two things. So those units that have the disintegrations per minute per gram of carbon and minutes per gram of carbon, they actually cancel out because it's the same mathematical as dividing them. So that's why you don't have to worry about those units. So here our units of time is really based off of the decay constant units there of the year. And those really are in this equation, when you use the kinetics equation, those are really the two that you should sort of worry about in terms of units. The other ones you should also worry about, the 2A's, as long as they are though in the same units, then they'll sort of cancel each other out in terms of whatever units they are in. Or like the previous problem, if we had one that was in milligrams, when we would get the answer, it would be in milligrams and so forth and stuff like that. Other questions on that? All right, so obviously at this point, we do know our formula here to use. We have our half-life, in this case, still the same. So once again, as a question earlier, we would use the same half-life there since it is still carbon. Obviously, if it wasn't carbon, you would use the half-life for whatever element it would have been. In this particular case, that basically will give us the exact same decay constant as what we had before through the exact same calculation, basically taking the natural log of 2 divided by 5730 years will get us the exact same guy. In this case, we have a living sample giving us a rate. So living would be initial, 20 counts per minute per gram of carbon. We're looking at how many counts will be there at the end. That's sort of our final. In this case, they did give us the time of 15,600 years. So the time here and our decay constant are also in the same units. So that again is good. So that would give us the natural log of A is equal to the natural log of 20 minus our 0.00121 years times the 15,600 years. Years here will cancel. We could clean up the right-hand side there. And that would get us natural log of 20 minus 0.000121 times 15,600. Looks like a 1.10813. Once again, we're going to E both sides there. That gets rid of that. A would then equal about 3.03. The units here would match the units of our initial, which would be counts per minute per gram of carbon, basically, which again is just another sort of radioactive decay rate, like the other one. Does make sense. The initial guy was 20, right? So this guy should be decayed a while, so it should only be giving off less counts per minute per gram of carbon. Again, if you got more, then you did some math wrong. Any questions on kinetics and radioactivity? Yeah. What's that? Yeah, it would probably be given to you. I would say maybe in a book, it might not be given to you. You may have to look it up or something like that. But again, you would just look it up like that table that we saw there for whatever the element would be. But usually some type of dating would be some type of carbon dating or the other one there, which was the uranium dating.